Narrator voiceover. Imagine a world where machines don't just process data, they understand it. Where algorithms don't just recognize patterns, but reason about them. This isn't science fiction. It's the cutting edge of AI research, where transformer architectures, neural scaling laws, and emergent capabilities are rewriting the boundaries of what's possible. Today, we're diving deep into the latest breakthroughs shaping the future of artificial intelligence. Segment 1, the evolution of neural architectures. Let's start with the foundation, transformers. Introduced in 2017, these models replaced recurrent neural networks by using self-attention mechanisms to process sequences in parallel. But here's the twist, recent advancements have taken this a step further. Researchers are now experimenting with sparse attention, where models dynamically allocate computational resources to the most relevant parts of a sequence. This isn't just efficiency, it's a paradigm shift in how we think about information flow in neural networks. Consider the implications. Traditional transformers struggle with long-range dependencies because their attention matrices grow quadratically with input length. New architectures like LongNet and Performer address this by approximating attention with linear complexity. By leveraging kernel methods or sparse connectivity, these models handle sequences up to 1 million tokens, think books, legal documents, or even entire code bases, without a performance hit. Transition. But how do these models learn to prioritize information? The answer lies in their training objectives and the data they consume. Segment 2, training objectives and emergent capabilities. Modern AI systems aren't just trained to predict the next word, they're optimized for tasks we haven't even conceived yet. Take the concept of scaling laws, a mathematical relationship between model size, data quantity, and performance. Studies show that as models grow, their capabilities don't just improve incrementally, they emerge unexpectedly. A 100 billion parameter model might suddenly exhibit reasoning skills or code generation prowess that weren't explicitly programmed. This isn't magic. It's the result of massive scale training on diverse datasets. But here's the catch, scaling alone isn't enough. Researchers are now focusing on alignment, ensuring models' objectives match human values. Techniques like inverse reinforcement learning and preference modeling are being used to fine-tune models with human feedback, creating systems that aren't just powerful but trustworthy. Transition. Yet even with these advances, challenges remain. Let's explore the roadblocks holding back the next generation of AI. Segment 3, challenges in modern AI research. First, there's the problem of generalization. While large models excel at tasks they've seen during training, they often fail in out-of-distribution scenarios. For example, a model trained on medical texts might struggle to diagnose a rare condition it's never encountered. To tackle this, researchers are experimenting with meta-learning and few-shot adaptation, teaching models to learn new tasks with minimal examples. Then there's the issue of interpretability. Deep learning models are often seen as black boxes, making it hard to audit their decisions. Recent work in neuro-symbolic reasoning and attention visualization is shedding light on how models process information. By combining symbolic logic with neural networks, we're creating systems that can explain their reasoning, critical for applications in healthcare, finance, and autonomous systems. Transition. These challenges aren't roadblocks, they're opportunities. And the next frontier. Integrating AI with the physical world. Segment 4, the future of AI, from simulation to reality. Imagine an AI that doesn't just analyze data, but interacts with the environment. This is where reinforcement learning and robotics converge. Projects like DeepMind's MuZero and OpenAI's Dactyl demonstrate models that learn to play games, solve puzzles, and manipulate objects, all through trial and error. But here's the breakthrough. These models are trained in simulated environments, allowing them to accumulate experience at scale before deploying in the real world. Another emerging area is neuro-symbolic AI, which merges the flexibility of neural networks with the rigor of symbolic reasoning. By encoding domain knowledge into structured representations, these systems can reason about causality, handle logical contradictions, and generalize beyond their training data. This is particularly vital for fields like scientific discovery, where models need to hypothesize, test, and refine theories autonomously. Closing. The future of AI isn't just about bigger models or faster processors. It's about creating systems that understand, reason, and collaborate with humans. From sparse attention mechanisms to neuro-symbolic architectures, the latest research is pushing the limits of what machines can do. But as we stand on the brink of this new era, one question remains. How will we ensure these technologies serve humanity's greatest good? Thanks for watching. If you want to stay ahead of the curve in AI research, hit subscribe. And let us know in the comments what breakthroughs excite you most. The conversation starts now.